Testing, testing, 1, 2, 3. 2, 3. 1, 2, 3. Testing, testing, 1, 2, 3. Okay, seems to work, and we are live. So I just decided to start the setup a little later instead of just pre-setting it up. Just if anyone decides to join us, they can join us ahead of time. And so what we have here, looking at a kinematic problem. And the problem we have, it says a cannonball is fired with velocity v. At what angle from the ground must the cannonball be fired in order for it to hit an enemy that is at the same elevation but a distance d away? Okay, so we basically have a setup like this. We have a flat ground, since it says we have the same setup. We have our cannon, which is ideally we're just going to estimate it's on the ground. This thing's going to shoot, and we basically want to find the angle of approach. We have velocity v, and we have our target, someone we do not like, and they are distance d away. And so what we want to find is what angle is needed to basically blast this person. And so the choices we have is arc, sine, v over gd, b, arc sine, gd over 2v, and 2, this is still arc sine, 2gd over v, still arc sine, and then this one's 1/2 arc sine, gd v squared, and e, which is arc sine gd over v squared. Okay, and so so to go the intuition route, we had totally bombed that last time. But it doesn't mean we should give up on that approach. But one thing I usually like to do, so within here, we know that the units, since we're looking for an angle, right? And sine typically requires some type of radian or degrees in. You should get a regular number out, right? So the number that goes in here, the unit should be unitless. And so when we look at this V over here, this is meters per second. And on the bottom, we have meters per second squared over D is a distance, meters. So this isn't going to cancel out to B1. Cancel here, here, one of this 2, and this S. And this gives us velocity in here. So anything that's just a V over GD or the other way around, I think we can cancel them out. So I don't suspect it's any of these actually. This one, or this one. But when you look at this one, GD, this is acceleration. This is a gravitational force. This is m over second squared times d, which is distance, times m divided by velocity squared, which is m squared over s squared. And so these will cancel out. So I suspect it's going to have to be D or E. And we're basically just going to have to find out whether there's a 1/2 factor or not, right? And so in terms of reaching into our, bags or pockets, let's try to think about this a little bit. Okay, what do we know? So we have an angle. So we recognize that there's going to be some trigonometry involved, right? We're going to make basic assumptions. There's no wind resistance. Um, and so the only force that's being applied here is the gravitational one, right? And um, in this case, if we were to use m, it actually wouldn't matter in terms of trajectory. And we could ask, well, why is that? Well, when we look at the sum of the forces, right? Um, we know that this is usually equal to ma. Let's say in just the y direction, right? Well, we know that the only force acting on this is gravity, which is going to be minus mg. And so when we look at these two, the m's cancel out. So the acceleration in the y direction is purely gravitational. And so we'll approximate it to be negative 10 m per second squared. But we're actually just going to want to keep it g, as we can see it's going to be g. And so we can just keep it at this for now. So a in the y is equal to minus g. Cool. That made our efforts really easy, right? And so now for the uh, x direction. And so I just pull out the sum of the forces. Normally, you can always apply some kinematic equation and get it right away. The approach I want to take is just use the first principles training that I have. And what do we always start with in physics? You just look at sum of the forces, conservation of energy. These are basic principles that'll take you far, right? So we know that there's actually no forces in the x direction, right? What this tells us is that there's the acceleration is equal to 0, right? We're assuming that this thing has mass, so ax is equal to 0. This doesn't necessarily tell us anything useful right away, but it does tell us that we have a constant velocity in the x direction, right? And so with this constant velocity in the x direction, it's going to be heavily influenced by this. And so how can we get this? We do have a v, right? And so this is where it comes into play. We have when we look at a sine and a triangle, right? Opposite over hypotenuse. I've probably said this before, the Sohcahtoa rule. We have a theta here. We know that this trajectory that we have the v, right? We're interested in vx. So how do we write vx in terms of this? Well, we could use our Sohcahtoa rule. And so we have hypotenuse and adjacent. So for Sohcahtoa, this, oh, and I guess maybe I should probably specify what this means. So just in case for some of you who don't know, Sohcahtoa, this refers to sine, cosine, and tangent. And so this kind of neat rule, it says opposite. So opposite is this one. O, H is hypotenuse of a right triangle, and A is adjacent. And so in this case, we have hypotenuse and adjacent. So we're going to use cosine for this, right? And so we have Vx is actually equal to V times cosine theta. Okay. Um, so let's see. Well, the thing is, we need to find a little something else out, right? Because for now, we don't really have anything that might translate immediately. But what we need to recognize is what's the time that's going to take this ball to go up and down is going to be based on our y. So let's play a little bit with that, right? What's the initial velocity our ball has? Because we want to look at time, right? So let's think about this real quick. If our cannonball is moving in the x direction with velocity vx, then in order to get to a distance d, we have to have the constant velocity times time, right? And so what we need to solve for is this time component. And so it's all going to depend on basically our cannonball going up and then going down. If you just purely look at it in the y direction, if you were just to shoot this straight up, it'd go up and then come down. And if you shoot it at a less like at an angle that's closer to parallel to the ground, more parallel to the ground, it has a smaller trajectory, and so the time frame is going to be smaller. So this t is actually going to depend on the angle of the trajectory in the y direction, right? And so let's think about this real quick. So the time it's going to take to go up and then down is basically the kinematic relationship in the y direction. And so here, when we look at this, the acceleration, well, would we get velocity? We'd get velocity by taking the integral of both sides with respect to time. So we could think of this acceleration as position and taken to the second derivative squared, right? Or it's taken to the second derivative, position to the second time derivative. And so we integrate this once. We get negative gt. We take it again, and it gets plus a velocity constant. And we take it again, and what do we get? We get this kinematic equation minus g over 2 time derivative squared plus initial velocity times t plus the initial position. So the initial position we're just going to set here at 0. So this should probably be y if we're just going to be talking about going up and down. It's going to be 0. Our initial velocity actually is going to be Vy, which in this case, kind of similar to the Vx, when we look at this Vy, how would we solve for this in terms of theta and V? We know that Vy, which is going to be plugged into here, this is going to be equal to V times sine theta. Okay? And so, remember what we were going to end up wanting to solve for is for this theta, right? And so, here, this is the starting position 0. This is the other starting position, or this is the final position actually. As time progresses, if we're just purely looking for up and down, when this first starts, if time's equal to 0, we start here, just purely in the y direction. And as this thing starts moving in time, it's going to start going up and up and up, because notice this is a parabolic trajectory. And then it goes up to a certain point, and then it's going to start going down. And so, notice in any parabola, there's a possibility of having 2 points across if you're assuming that you have it 0 starting up and going down. So there'll be 2 routes. There'll be a route at time t equals 0 and another time. So when we solve for this, we want to look at the final position 0. The starting position is at 0 as well. Vy times t. And so starting position is 0, final 0. So in order to solve for this, you can factor out the t, and we get g over 2t plus Vy. And so when you solve for, so what you see is that either this can be 0 or this whole thing could be 0 in order to make this true. When this is 0, it's just the initial time position. What we want is the time it takes to go up and then back down. And so that's when this is 0. So when we solve for this, we find out that Vy is equal to g over 2t. What we want to solve for is this t, and so we move this stuff over. 2Vy over g is equal to t. Coolio, my dude. And so let's look at this, and we get 2V sine theta over g. Okay. And so in the end, we still want to solve for this right here, right? This theta. Okay, let me take a step back. What is it that we're going to want to solve for? Yeah, no, I think we're going to want to solve for this theta, right? And so, again, with this t, one thing I'm curious about is where this is going to fall into play. Okay, let's just try it out and see what happens. Just because I'm a little skeptical of this one part. So when we look at this t, right? We solve for this t. We also get d is equal to b cosine theta t, and then we could say t is equal to dv cosine theta. And so we could plug these two together, and we'll get dv cosine theta is equal to 2v sine theta over g. Oh, I see. So there was a little something I was concerned about, and actually we're able to hash that out in a little bit, and I'll show you. Right? It's going to require a trigonometric kind of calculation. So what we want to do is move the things with the theta to one side and everything else to the other side. So we'll multiply both sides by g divided by 2v. And so what we end up getting is gd over 2v squared. And this is equal to sine theta times cosine theta. And so this is the part where I was concerned about. How the heck are we going to solve for theta? You have a sine and cosine. That's pretty confusing and a little bit weird and off-putting, to be honest. But there's a cool trigonometric substitution, right? That's going to come save the day. So there's a sine rule where it's sine alpha plus beta is equal to sine, cosine, cosine, sine. So sine alpha cosine beta. So if it was plus minus, it's plus minus cosine alpha times sine beta. And so the cool thing is here our alpha and beta are equal to theta. So this is sine 2 theta is equal to, since we end up dealing with the plus, this is sine theta, cosine theta, sine theta, which is the same, so you switch it. So it ends up just being 2 cosine theta times sine theta, or sine theta times cosine theta. They're the same thing. So when you end up dividing by 0, basically you have that sine theta. So from this side, let me just rearrange it. Sine theta cosine theta is equal to sine 2 theta divided by 2, right? Because we divided this by 2 and we rearranged this. And so this gets plugged into here. We get gd over 2v squared is equal to sine 2 theta over 2. So these two 2's cancel out. We basically then take the arc sine of both sides, right? We get arc sine. And so arc sine is basically the inverse of sine. Arc sine gd over b squared is equal to 2 theta. And then you divide both sides by 2. And you get theta is equal to 1/2 arc sine gd over b squared. Let's check our work real quick. And boom! We have one of these responses, D. That's what we got right here. Good work. Okay. And so notice, I'm deriving a lot of these steps. If you really want to, get this done, this has to be done in a relatively quick time. So I'm just trying to learn this stuff and get back in the habit. Once we get down to the real training, as it gets closer to the time, to the GRE time, we'll go over techniques. So right now we're just kind of having fun relearning this. I'm revisiting a lot of these physics concepts. I haven't seen them in a while, but it doesn't mean we can't tackle them and work through them together. So if y'all have any questions, feel free to make a comment somewhere. I'll find it and respond. And if you have other interesting problems, I'm willing to work on those too. Shoot, we'll work on your homework together if you want. Um, but yeah, no. In the meantime, I hope y'all are enjoying this series, and once I get a little more organized with some of this stuff, we can just work on other problems together and keep learning. All right, but until then, keep shining, do your thing, and bye bye.